The conventional band diagram, as shown in the screen, shows only the band gap energy. But EK or EP diagram, which is energy versus momentum diagram, shows the relationship between energy and momentum of electrons of available states in the material. This diagram helps in understanding the optical properties of materials. We will study a simplified version to have a little insight of what are energy momentum diagrams. The actual concept is obtained by solving Schrodinger's wave equation and Heisenberg's metric mechanics, which is quite complex and requires advanced mathematics and good knowledge of quantum mechanics as well. We know that energy of a free electron can be given as E is equal to p square upon 2 m naught, where p is momentum and m naught is the free electron mass. But in a crystal where there is a periodic rise and drop of potential, free electron mass cannot be used. In a crystal, m naught is therefore replaced by mn, where mn is effective mass of an electron in semiconductor. The effective mass of a particle in a crystal is a measure of how its momentum changes with applied forces, and it plays a crucial role in determining the electrical and thermal properties. Effective mass of electron can be defined for different semiconductors. Effective mass is actually a property of particular energy band. Therefore, electron can have different effective mass for the same semiconductor if the difference between energy bands is significant. Now, after modifying the equation, we will get E is equal to p square upon 2mn. If we plot the graph of E versus P, then we will get a parabola. Here we have a rough sketch of parabola, where on y-axis energy is represented and on x-axis momentum is represented. One important skill a student should have is to interpret the data provided in any graph. Now for example, assume there is a semiconductor in which there are only 6 electrons whose energy momentum diagram is represented as shown. Now, what information about electric current you can get from this graph? First, you try on your own. We know that electric current is caused due to movement of electrons. But here, if we add the momentum of all electrons, the expression will be P1 plus P2 plus P3 plus P4 plus P5 plus P6, which in short can be written as summation of momentum of all the electrons. This dashed line signifies that the two electrons on its extreme has equal magnitude but have different directions. If one is positive, then the other is negative. It means that velocity of electron 4 and 3 has equal magnitude but are opposite in direction, resulting in cancelling out each other, making net current 0. It simply means that if electron 3 is having say 1 ampere current, then 4 will have minus 1 ampere current, cancelling each other. Similarly, fifth electron will cancel out the effect of second electron, and sixth electron current will cancel out first electron current, making net current 0 inside the crystal. So here you can write the momentum of all the electrons is 0, meaning that net electron current is 0. Now we have another EP diagram in which we have considered 5 electrons, and you have to tell what will be the direction of electric current in a crystal if we assume that there is a crystal and this direction is taken to be positive velocity of momentum. Means that if the electron is flowing in this direction, then it will have a positive magnitude, and if in this direction it moves, then the momentum will be negative. This is conduction band and this is valence band. We assume that all the electrons are present in conduction band. Now just tell me in which direction the net current will flow, in right or left. It is shown in the diagram that the magnitude of momentum of the 5 electrons is negative. So the electron will be moving in left direction. But we also know that the electric current will be in opposite direction to the flow of electrons. Therefore, net electric current will be in right direction. Hoping you got some clarity about energy momentum graph, we move forward. We know that energy is equal to P square upon 2mn, where mn is the effective mass of electron as we have already discussed. Now we will differentiate energy with respect to momentum, giving now we will differentiate this expression with respect to momentum again, giving us we got another very important expression. What data does it hold for us, and why do we even need this? To understand this, we will take some help from simple mathematics. Let's say we have two lines y is equal to m1x and y is equal to m2x, and two graphs are also provided, but it is not known that which graph belongs to which equation. Assume that m1 is greater than m2. Now, is it possible to tell which graph belongs to which equation? First, we will differentiate the first equation with respect to x, giving us m1. Similarly, we will differentiate the other equation of line, giving us the slope m2. Since you already know that this angle theta is nothing but tan inverse m, where m is the slope of the line. Also, we know that as m increases, theta also increases. It is provided that slope m1 is greater than m2. Therefore, theta 1 will be greater than theta 2. It means that the bigger angle is theta 1, making this graph to be y1 is equal to m1x and this graph equal to y is equal to m2x. Similarly, we will now examine two different equations which are y is equal to m1x square and y is equal to m2x square. You know that both these equations represents a parabola with vertex at origin. It is also provided that m1 is greater than m2. We are having the same question which we solved earlier, that which graph represents which equation. We will differentiate both the equations of parabola with respect to x, giving us 2m1x and 2m2x. In this case, we will assume any point x1 on the x-axis and make a dashed line parallel to y-axis so that it cuts both the graph. Now we will make a rough slope at the points the dashed line will be cutting the two graphs. Let's say this angle to be equal to theta A and this angle to be equal to theta B. We have m1 greater than m2. From the graph we can see that theta B is greater than theta A, and from the previous case we can say that the equation of the line with higher value of coefficient will have higher value of theta. It means that theta B is equal to theta 1 and theta A is equal to theta 2. It means that this graph is of y is equal to m1 x square, whereas this graph is y is equal to m2 x square. It means that if we are having two parabolas, then the one which is having higher coefficient of x square will be narrower. I hope this concept is clear to you. Now we come back to this equation and try to answer the previous questions, which were what data does it provide and why it is needed. While clearing the concept, we were talking with respect to y and x, but here we have energy and momentum. So we can say that higher the coefficient of p square, narrower will be the parabola. From the equation, coefficient of p square can be easily found to be equal to 1 upon 2 mn. It means that coefficient of p square will increase as mn will decrease, as they are indirectly proportional. Summing up all the points, we can say lower the effective mass, narrower the parabola. This is the most important point which you have studied so far in this lecture. We have discussed quite a bit about EP graph of an electron. However, EP graph is also drawn for holes as well. The difference being the coefficient of p square, which is 1 upon 2 mp, where mp is the effective mass of hole. Generally, the effective mass of hole is greater than effective mass of electrons. However, this cannot be said to be true for all the semiconductors. We answered the first question about why we differentiated the energy with respect to momentum. Now we will answer why we need it. Few of you might be thinking that if we are supposed to deal with the coefficient of p square only, then why we differentiated the energy with respect to momentum at the first place. The thing is, 1 upon mp is actually the slope of the line which we discussed in mathematics. There can be different way in which a single thing can be explained. I tried to explain you why drawing a rough slope on the two parabola. However, another way of explaining it is by differentiating the parabola to find equation of line, then differentiate it again to find the slope of the line and comparing it afterwards. There is one more reason why we differentiated the energy. However, it will be discussed in the next lecture. The question of what is answered. Now why is remaining. We needed that expression to draw energy band diagram in which effective mass of electron and holes are different. To know which graph will be narrower, we need this concept. Suppose if you are asked to draw energy momentum diagram for a semiconductor, then not only electrons are considered but holes are also considered. Suppose there is a conduction band. Here we have valence band. We have E is equal to P square upon 2mn, and here we have E is equal to P square upon 2 MP. You can see even though we have two parabola, but they are not exactly the same. One will be narrower, and which will be narrower, as we studied already, that the graph for that particle which is having a smaller effective mass will have narrower energy momentum graph. Therefore, for general case where effective mass of hole is greater than effective mass of electron, this diagram is valid. Few important points which you should keep in mind. First is, electrons are usually represented by black dots, and if an electron transition take place, then these electrons will be shown in the conduction band, and the vacant place will be represented by a circle representing holes. This is Mn, not Me. Another important point you should remember, that usually energy momentum diagram are shown by just two parabolas. Neither the x-axis is shown nor the y-axis is represented. But it should be naturally clear to you that if we talk about energy, it is a relative quantity. We set the reference of energy somewhere in between the conduction and valence band, so that one energy band will have positive values and other will have negative values, which will eventually result in two parabolas whose vertices are facing to each other. If you see any diagram like this, then you can tell that effective mass of electron is smaller than effective mass of hole. You should not be confused about which axis is representing which quantity, because you already know energy is represented on y-axis, whereas momentum is represented on x-axis. And since it is already said to you that it is energy momentum diagram, then you should not panic if x and y axis are not represented. I hope the concepts are clear to you.